Good morning all. Good to see you again. Here we have a Homag Spindle motor. And this thing will get up and go. Its max speed is 24,000 revolutions per minute. Shoo, that's moving. Yeah. It's manufactured by Homag. Its model number is HSK-63F. Its part number is 2-056-16-6200. We're going to look at the feedback device. It's a transducer pickup that outputs an A-B sine wave. 1 volt peak to peak on the sine A and the sine B. It's just like an encoder. We'll see the 90-degree phase shift between A and B. We'll see a 180-degree phase shift between A and A bar and B and B bar. It takes 5 volts to power up the encoder. And so we'll power it up and we'll look at it with the oscilloscope. We'll look at the A-B sine wave and their relations between each other. We'll also measure the amplitude. The data sheets for these transducer encoders state that the peak-to-peak voltage is 1 volt, riding on 2.5 volts. We will see a sine wave, and its peak-to-peak voltage riding on that 2.5 volts should be 1 volt. We'll see what that amplitude is, peak to peak. Let's get started. We want to set up our power supply for 5 volts DC. We're going to apply positive 5 volts to the red wire on this connector right here. We're going to take the 5 volt ground and connect it to the blue wire. And then A is the white wire, and B is the brown wire. No, that's not right. I'm getting ahead of myself. A is the white wire, B is A bar. I did it again. Phew. I can't think straight since I had my stroke. We're still on this side of the dirt. About 75% functional, brain-wise that goes. So, let's try it again. A is the white wire. A bar is the brown wire. B is the violet wire. And B bar is the black wire. And like I said earlier, the red wire is plus 5 volts, and its ground is the blue wire. There we go, we got it that time. I think in about 10 years my brain will be back to 100%. We'll see. Shoo-wee. Okay, let's hook everybody up. Turn this power supply off. It's set to 5 volts DC. There's our red lead. There's our black lead connected to the power supply. Use different colors for your power supply connections. That way you won't get them hooked up backwards. And try to use the same colors every time. That way you won't get yourself confused. Let's go over here and grab these clip leads. We're going to hook our scope to the power supply ground. We've got a brown clippy lead right here. That's going to go to the blue wire ground. Let's get out of the way here so you all can see. There's our blue wire. We're going to take our purple lead. We're going to connect that to 5 volts, and then that's going to get connected to the red wire over here on this connector. So that takes care of our 5 volts and ground. Now for the scope of probes. I've got 2 scope probes, one for A. Channel 1 will be for the A, and channel 2 will be for the B. So we'll take our blue clip lead, that is going to connect to A, so it pins right there. And to start out with, we're going to look at A and A bar in relation to each other, but let's go ahead and do A and B first, and then A bar and B bar. And we'll check for the 90-degree phase shift. So we got channel 2 of the scope connected to B. Let's see what we get real quick. There we go. That looks good. Okay. Let's get the camera here in front of our scope screen and you can see what's going on. Here, the top waveform is going to be A, the A sine wave. The bottom waveform is going to be the B sine wave. And we apply 5 volts to the encoder. Those waveforms will rise up to 2.5 volts. Right here is ground of the A sine wave, and here's ground of the B sine wave. Let's apply 5 volts to the encoder. You can see that they have moved up from here to here. It's about 2.5 volts, and from here to here is about 2.5 volts. Now I'm going to rotate that spindle motor shaft. Get going. There we go. You see that? We have the A sine wave and the B sine wave. Now both sine waves are 90 degrees out of phase with each other. We're going back the other way. We can see, if I could rotate at a constant speed, we can see that B leads A when I'm going counterclockwise. Let's go back the other way. And now A leads B. Okay, I'm going to power down and move channel 1 to A bar and channel 2 to B bar. Let's power back up. I'm rotating clockwise. Let's go counterclockwise. Clockwise again. It acts identical to a quadrature encoder. The only difference is that we have a sine wave output. The reason it's a sine wave output is because it's a transducer. Instead of an optical encoder, this uses a pickup. And the reason they use a pickup, because at such high speeds that these motors run, if you had a glass code wheel or a plastic code wheel, it would fly apart from centripetal force. It would just shatter. There's no way it could withstand those forces placed upon it. Let's rotate again. Okay, what I'm going to do, I'm going to superimpose the A waveform on top of the B waveform, and we'll see the phase shift. Let's bring that down so that they both overlap each other. That looks pretty close right there. Can you see the phase shift? Let's get a little bit closer lined up there. Not too far. Get up there. How's that look? There's our phase shift. Let's go back the other way. That's our 90-degree phase shift. The A and B are 90 degrees out of each other. Okay, let's bring channel 1 back up. Okay, that was A and B, and A bar and B bar. Now, let me power down. We're going to look at A and A bar. And these two waveforms will be 180 degrees out of each other. A phase shift of 180 degrees. There we go. We're back up to 2.5 volts. Let's rotate. Look at that right there. The top waveform and the bottom waveform are 180 degrees out of each other. They're opposite of each other. Alright, I'm going to power down. We're going to look at B and B bar. And they also will be 180 degrees out of phase. The top waveform is B. The bottom waveform is B bar. Now again, let's superimpose A on top of B. And you'll easily be able to see the 180 degree phase shift. See that? Looks like a chain necklace. Okay, let's go back up. Okay, we're back up on ground right there. We're 2.5 volts above ground. And right here, the second channel of the oscilloscope is 2.5 volts above ground. A and A bar, B and B bar are complements of each other. Okay, now what we're going to do, I really like this feature of this oscilloscope. Let's move channel 2 out of the way so we're only looking at one channel. There we go. We're looking at the channel A right here. That would be, right now, that would be B, the B sine wave. And I'm going to select up cursor measurement. We're going to do H bars, and we have 2 bars that we can move with this dial, and that, select up the other one, we'll be able to measure the peak-to-peak value here. Let's bring that up. Whichever line is solid is the one that the dial is going to move. So we're moving that one. We select the second line, it goes solid, and we can move that one. And the distance between the two lines is displayed on the screen. So let me rotate, and we'll try to line up. There's the top. Let's bring the bottom up. And there's the bottom. A little bit more. That's pretty close right there. And from peak to peak, we have 660 millivolts. Well, that's not quite a volt, is it? We can bring up that bottom just a little bit more. There, now we've got good. The lines are touching the positive side and the negative side of the sine wave, the peak to peak, and it says we have 620 millivolts, and it's 2.14 volt above ground. So from here to the center of the sine wave is 2.14 volts, and the peak to peak of the sine wave is 620 millivolts. Those specs don't line up with the data sheet, do they? We're supposed to have a 2.5 volts above ground and 1 volt peak to peak. Not quite the same as the data sheet. But as long as the system that encoder's connected to would convert this sine wave to square waves, it would probably be good. Be interesting to see how this motor feedback works in the machine. Are the sine waves translated to proper square waves, or because we're only 620 millivolts peak to peak, will it fail? Interesting. Well, there you go. Okay, let's turn those off. We'll turn channel 2 back on. Let's move the menus out of the way. And each grid on the y-axis is 1 volt per division. So we have 1 volt per division on channel channel 1, and 1 volt per division on channel 2. All right, let's power down. We're done with that. What'd you think of that, folks? Wasn't that fascinating? I like doing little tests like that. I'm worried about that amplitude, though. I'm worried about that amplitude. I wonder if that's adjustable. If we move the transducer pickup closer to the gear teeth that it's sensing off of, would the amplitude increase? And if we move it away from the transducer pickup, would the amplitude be less? So when it's adjusted closer, we might be able to obtain 1 volt peak to peak. Huh. Well, maybe someday we'll climb into this motor and see if we can adjust it closer to the gear teeth pickup. Move the pickup closer to the gear teeth. We'll save that for another day. Okay, on to the next job. Don't run off yet, people. We got more to do. Let's unhook our hookups and we'll move this motor out of the way. We'll bring in the second job. See you in a little bit.